In this video, we're going to work through some examples of using the method of undetermined coefficients to solve second-order linear non-homogeneous ODEs with constant coefficients. The main technique here is to first assume the form of the solution, plug this into the ODE and match the coefficients from the left-hand side of the equation with those on the right to get our final solution. The biggest challenge is knowing which form the solution will take. Here we have an example of the right-hand side of our non-homogeneous ODE, and next to this we have the function that we should guess as being the correct form of the solution. Before we get into some examples, I want to highlight 5 tips so that you will always choose the correct form. Let's concentrate on these 3, the polynomial, the exponential, and the sine-cosine functions. Tip 1. If our right-hand side is a polynomial, always guess a solution that takes the general form of a polynomial to the same degree. So here we have a polynomial of degree 2, so our guess will be the general form of a polynomial to degree 2. Tip 2. For exponentials, keep the guess in the same form as your right-hand side, but always include a constant. This is because if we take the first and second derivatives of exponentials, this is the form it will take. Tip 3. For sine and cosine terms, make sure that your solution includes both a sine and a cosine term. Because if we take the first and second derivatives, sine becomes cosine and then minus sine, and cosine becomes minus sine and then minus cosine. So we need to cover all possibilities in our solution. Tip 4. If our guess is actually a solution to the homogeneous equation, multiply the guess by x and try again. We'll cover an example of this as well. Tip 5. If you're ever unsure, include more terms and constants, not less. We're going to get the problem wrong if we don't include enough terms, but worst case scenario for including more terms is that some of them will be redundant, but not incorrect. Okay, so let's get to some examples. Here we have a second-order linear non-homogeneous ODE with constant coefficients, so we can use the method of undetermined coefficients. The first step is to guess the correct form of the solution. To do that, we look at the right-hand side of the ODE, x e to the 3x. So our right-hand side is a combination of a polynomial of degree 1, so the guess needs to include the general form of a polynomial of degree 1, so ax plus b, where a and b are some constants. And it also includes an exponential. So recall for exponentials, our guess will take the same form, but include a constant as well that we'll call c. Multiplying these two guesses, we get c e to the 3x times ax plus b. So we can actually drop the c here because as it stands, each term already includes a constant thanks to a and b. So our guess is e to the 3x times ax plus b. Step 2 is to plug this guess into our ODE and find the coefficients. To do that, we let y equal e to the 3x times ax plus b. That was our guess. And now we're going to need to take the first and second derivatives. So if we expand y, then y prime becomes a e to the 3x plus 3ax e to the 3x plus 3b e to the 3x. And then that means y double prime is 3a e to the 3x plus 3a e to the 3x plus 9ax e to the 3x plus 9b e to the 3x, which can be further simplified to 6a e to the 3x plus 9ax e to the 3x plus 9b e to the 3x. Now notice that y prime and y double prime have 2 different types of forms. We have a polynomial x multiplied by the exponential, and some of the terms just have exponentials. So if we can separate these 2 different types here, that'll make our job easier later on. So I'm going to rewrite this as 9ax e to the 3x plus 6a plus 9b times e to the 3x. Now we can plug in y prime and y double prime into our ODE. Our job is to now split up all the terms that include the exponential and polynomial and the terms that only include the exponential so that we can match the coefficients with the right-hand side of the equation. Now it's just a matter of rearranging and simplifying. Okay, now that we have simplified it as much as possible, we can match the coefficients. Because the coefficient on the right is 1, we know that 2a must equal 1 if the left-hand side is to match the right-hand side, and that just means that a equals a half. We also know that we don't have any terms that don't include our polynomial x, so this tells us that 3a plus 2b must equal 0. And since we know a, then b must equal minus 3 over 4. So plugging our values of a and b into our initial guess of e to the 3x times ax plus b, we get our particular solution y sub p equals e to the 3x times a half x minus 3 over 4. Now, we're not done yet, as our full solution also needs to include the solution to the homogeneous ODE as well. So we also need to use the characteristic equation method, and I'll put a link up that shows you how to do this if you don't know. Using the characteristic equation method, we'll find that lambda 1 equals 2 and lambda 2 equals 1. So we get y sub h equals c1 e to the 2x plus c2 e to the x for some constants c1 and c2. So now we can write that y equals y sub h plus y sub p, which equals c1 e to the 2x plus c2 e to the x plus e to the 3x times a half x minus 3 over 4. And that's our final solution. Let's do another example. Here we have another second order linear non-homogeneous ODE with constant coefficients, so we can use a method of undetermined coefficients. Looking at the right-hand side of our ODE, we have an exponential term. So for exponentials, we should guess something that takes the same form but also include a constant, because every term needs to have a constant. So our guess is a e to the 2x. Step 2 is to plug this into the ODE. So we can let y equal a e to the 2x, then y prime equals 2a e to the 2x, and y double prime equals 4a e to the 2x. Plugging these into our ODE and simplifying, we just get that 0 equals e to the 2x. And this is a problem. Our left-hand side needs to equal our right-hand side for all values of x, but in this case there isn't even one value of x that can satisfy this equation. But imagine if our right-hand side was 0 instead of e to the 2x. Then we would have an identity and therefore a solution. So a e to the 2x is actually a solution to the homogeneous part of our ODE, but not the non-homogeneous part. So we need to modify our initial guess. So going back to step 1, we can multiply our initial guess by x. Step 2 is to let y equal our new guess, and then find y prime and y double prime. Plugging these into our ODE and simplifying, we get a e to the 2x equals e to the 2x. Matching coefficients on the left with those on the right, we can see that a must equal 1. So plugging in a equals 1 into our guess function, we get y sub p equals x e to the 2x. Now we just need to solve the homogeneous part of our ODE to find y sub h, and then we can add y sub h plus y sub p together to get our final solution. Using the characteristic equation method, we find that lambda 1 equals 2 and lambda 2 equals 1. So our homogeneous solution, y sub h, equals c1 e to the 2x plus c2 e to the x for some constants c1 and c2. Notice that our c1 e to the 2x is exactly the same as our initial guess a e to the 2x, because a and c are both just some constants. That's why we needed to modify our initial guess, because it was actually a solution to the homogeneous part of the equation, but not a solution to the non-homogeneous part of the equation. So now our final solution is y equals y sub h plus y sub p equals c1 e to the 2x plus c2 e to the x plus x e to the 2x. Let's do two slightly harder examples of guessing the correct form of the solution. Here we have the right-hand sides of two different ODEs. For the first one, we can just split up the terms. So our guess for the first term is a e to the minus 4x. The guess for the second term would be e to the minus 4x times b cosine of 3x plus c sine of 3x. And for the last term, it would be d cosine of 3x plus e sine of 3x. And we can just add all these together to get our final guess. Now, before we do the same thing for our second guess, notice that in both terms we have a polynomial multiplied by a sine or cosine term. Sine and cosine terms have the same guess function, so the two terms can actually be treated the same. Let's also pretend that the x is an x squared, because at worst we will have constants that go to 0, so it won't change our final solution. And now we can factor out the x squared, so we get x squared times cosine of x plus 9 sine of x. Now we can guess ax squared plus bx plus c for our polynomial function, and we can guess d cosine of x plus e sine of x for our sine and cosine terms. And this is our guess, which we can also write as ax squared plus bx plus c times cosine of x plus dx squared plus ex plus f times sine of x. In summary, find the homogeneous solution y sub h first using the characteristic equation method, so that when we guess our non-homogeneous solution, we'll know if we need to multiply it by x or not. Second, find the particular solution, y sub p, using the method of undetermined coefficients by carefully guessing the form of the solution, plugging it into the ODE and matching the coefficients on the right side of the equation with those on the left. Then plug these values for the coefficients into the guess function. And the last step is to write y equals y sub h plus y sub p to get the final solution. If you liked the video, then please give it a thumbs up. If you found it helpful, then feel free to subscribe. I make regular videos on calculus, linear algebra, statistics, psychology, and physics. As always, thanks for watching.